So our next speaker is Zhao from Stanford University. He's going to be presenting his work entitled Sigma, Compiling Einstein Summations to Locality-Aware Dataflow.
Hello, everyone. Excuse me.
Yep.
Okay, so in this talk, I will be presenting Sigma that compiles Einstein summation expressions down to locality-aware dataflow. So first, we introduced the concept of reconfigurable dataflow accelerator, known as the RDA. It allows users to exploit both vector-level parallelism and pipeline parallelism. During runtime, users can operate on stream of vector that gets entered into a processing pipeline consisting of both vector computation units and memory units. An RDA architecture contains the following components. First, vector computation units capable of processing vectors and tensors. Off-chip memory such as DRAMs. On-chip SRAMs that can be processed at vector granularity and can be used to store tensors. Vector FIFOs between these units. And pipeline registers within a computation unit. These pipeline registers are typically organized over 2 dimensions. Pipeline dimensions for users to exploit pipeline-level parallelism, and vector dimension for users to exploit vector-level parallelism. Furthermore, these on-chip resources are connected using a fully pipelined vector interconnect. First, we show that RDA compilers, such as the previously proposed spatial language, utilize bandwidth from large memories with small bandwidth. First, we show this capacity versus max attainable bandwidth trade-off curve on an RDA system. We see that for large memories such as DRAMs and vector memories, these memories have the largest capacity, but are typically small, but can offer typically smaller maximum attainable bandwidth compared to finer-grained memories such as, say, vector FIFOs and pipeline registers. However, data transfers between DRAMs and vector memories are typically explicit in existing RDA languages. Here, we show an example of an RDA program implemented in spatial. Users typically declare on-chip memories explicitly. Here, mem0, mem1, and mem2 gets mapped to on-chip memory units. And then code in terms of loops such as loop 0 and loop 1 gets mapped to on-chip computation units. In this example, memory accesses such as the traffic between DRAM and on-chip memory is explicitly managed by the user. On-chip element-wise data accesses are also explicitly managed by the users. In this example, the FIFOs are implicitly created. And existing RDA languages, such as spatial, typically assume that a vector FIFO unqueues a vector per each clock cycle and dequeues a vector per each clock cycle. However, we argue that this kind of assumption could potentially create an issue. For example, let's say that in this example, we want to duplicate loop 0. In order to feed enough of data into, say, the n copies of loop 0, we also have to duplicate the memory to provide enough bandwidth. And this could potentially lead to a waste of on-chip memory resources. In Sigma, we try to utilize bandwidth from small memories with large attainable data bandwidth and to try to solve this issue. And in Sigma, we mostly focus on data transfers between vector memories to vector FIFOs and vector FIFOs to pipeline registers. And the data transfers between these finer granularity memories are the first-class citizens for bandwidth utilization. Furthermore, we relax the assumption of the behavior of these implicit vector FIFOs. We assume that instead of, say, only unqueuing vectors and dequeuing vectors per each clock cycle, we assume that a vector FIFO can unqueue n scalars per each clock cycle and dequeue n scalars over the period of n clock cycle. By doing so, we are able to implement a time multiplex memory unit access. Here, for the same example, we're looking at, say, trying to feed n vector FIFOs by using 1 memory unit. We can implement the following with the relaxed FIFO model. For example, at cycle 0, we could use mem1 to unqueue a vector into the first vector FIFO. At cycle 1, we can further use the mem1 to go ahead and update the second vector FIFO, while at the same time, the first vector FIFO starts to dequeue a scalar. And we keep doing so until cycle n-1, where map1 starts to send a vector to the last vector FIFO, and then the first vector FIFO has already dequeued n scalars over the period of n cycles. So this allows us to translate these in-space mappings to in-time data reuse. Namely, we can use one map1 to update multiple copies of loop 0 on the computation units, which allows us to save the memory resources. To implement this strategy, we propose a heuristic-based mapping algorithm for data reuse. The input to the algorithm is an Einstein summation expression that contains sets of dimensions, two tensors, and sets of dimensions where reduction happens. We first find the reuse of each tensor dimension between two tensors. Second, we map the tensor dimensions with the largest data reuse to the vector dimension, given that most of RDAs have much larger vector sizes than the depth of pipeline stages. Last, we map the other tensor dimensions with data reuse to the pipeline dimension so that we can have a tight pipeline execution schedule. Here we show an example of mapping a convolution 2D to a computation unit. For the given Einstein summation expression, we have the following dimensions: kh and kw, the kernel dimensions; h and w, the dimensions of the image tensor; IC, the input channel of the image tensor and of the filter; and OC, the output channel of the filter. To perform the first step of our heuristic-based mapping algorithm, we first divide all of the tensor dimensions into three categories: dimensions that only belong to the image tensor, h and w; dimensions that only belong to the filter tensor, OC; and dimensions that have been shared between the image tensor and the filter tensor, kh, kw, and IC. First, we try to find the data reuse between the image tensor and the filter tensor along the dimensions kh, kw, and IC by fixing the indices iterating over all of the other dimensions. In this example, we can see that an element within the image tensor gets mapped to an element within the filter tensor over these three dimensions, kh, kw, and IC, and therefore there's no data reuse between these two tensors along these three dimensions. Next, we try to find the data reuse along the OC dimension by fixing the indices iterating over all of the other dimensions. And by doing so, we find that one element within the image tensor gets reused by OC elements over the filter dimension. And we can keep applying this strategy iteratively over all of the other dimensions, h and w. And we can see that the data reuse of the filter tensor with respect to the image tensor is h over the h dimension, and the data reuse of over the w dimension is w. In this example, so far, we have identified three dimensions that give us data reuse. Data reuse over the h dimension is h, and data reuse over the w dimension, and data reuse over the OC dimension. And given that h equals to w and less than OC, here we know that the OC is the dimension that gives us the most data reuse, and should be mapped to the vector dimension of a CU. And then last, we map the other tensor dimensions with data reuse to the pipeline dimension. And the remaining dimensions here, still with data reuse, are h and w. And since h equals to w here, we pick h as the first dimension that we want to map over the pipeline dimension. And during execution, we could simply streaming one column from the h dimension into the innermost CU. And then once we completed execution over one column of the image tensor, we can bring in another column. Noticing that at this step, we still have some dimensions that has no data reuse, namely the kh, kw, and IC dimensions, and we still need to map them. The strategies for mapping these dimensions are that, number one, we want to unroll smaller tensor reduction dimensions over the pipeline stages, and number two, we set the rest dimensions to be the outermost iterations of this mapping. In these three dimensions, kh, kw, and IC, the kernel dimensions are the reduction dimensions, and therefore we fully unroll them and then map it over the pipeline stages over these CUs. In this example, we show an example where, in this example, we have kh equals to kw equals to 3, and that the pipeline stage, and that each CU has 6 pipeline stages, and therefore after unrolling KH and KW, we need to map it to 2 CUs. And at last, we need to set the rest dimensions, which is IC, to be the outermost iteration. And in this example, we would simply execute the innermost mapping by IC times in order to complete the execution of this program. So that completes our analysis. To evaluate the performance and the benefits of Sigma, we configure a variant of plasticine RDA to have 200 vector computation units, 200 vector memory units, 16 vector dimension, and 6 pipeline stages over the pipeline dimension. We compare our results against a baseline accelerator implemented on Tesla V100 using PyTorch. And both Tesla V100 and plasticine RDA uses HBM V2 as the DRAM technology, meaning that both of them have roughly the same DRAM bandwidth. We evaluate these 2 systems over a wide variety of applications. And for each application setup, we choose a small problem size that would favor a small accelerator such as plasticine, and a large problem size that would favor a large accelerator such as the Tesla V100. First, we show that for data flow-rich applications such as Black-Scholes, decision tree, and random forest, plasticine is capable of outperforming the V100 on the small problem setup, and it roughly matches the performance of V100 on the larger setups. And this is because with Sigma, we are capable of better utilize the data flow-rich nature of the applications and then map them to a data flow accelerator such as plasticine. We observe roughly the same pattern when mapping to the GRU and LSTM applications, and noticing that since these applications have higher data reuse, plasticine roughly matches the performance of V100 on the large setup of GRU and LSTM. And lastly, for the convolution applications, we show that plasticine combined with Sigma is capable of outperforming V100 on convolution 2D and 3D. And furthermore, we observe a huge improvement over the convolution 4D baseline, but we conjecture that most of the benefit comes from the fact that we were only able to find a convolution 4D implementation online that requires multiple invocation of finer granularity kernels on the GPU. At last, we show speed up versus hand-optimized RDA programs normalized over the number of vector memory units, and this gives us a better idea of the benefits that Sigma brought over vanilla spatial. So when normalized over the number of vector memory units, we see on average about 40x speed up over the vanilla spatial program. And the benefits come from 2 dimensions. First, since Sigma is capable of utilizing the bandwidth coming from the finer grained memories better, we see 16x speed up coming from the vector dimension. Furthermore, since we are using fewer resources for implementing the innermost loop, we could unroll the outermost loop further to gain more performance. And these 2 factors combined together give us roughly 40x on average over the vanilla spatial implementation. Overall, the key takeaway for this talk is that fine-grained memories should be the first-class citizens for audio programming interfaces, since they provide more than 10x maximum attainable bandwidth compared to coarse-grained memories such as on-chip SRAMs or DRAMs. And with that, I'm open to questions.